Good afternoon, everyone. My name is Shreya Gupta, and I'm thrilled to be here today to talk about a truly transformative trend in the world of artificial intelligence: serverless AI's rise, revolutionizing ML deployment with scalability and cost efficiency. Over the next 25 to 30 minutes, we'll explore how serverless computing is not just an incremental improvement, but a paradigm shift in how we manage and deploy AI solutions. We'll see how it is enabling organizations to build and scale AI's application faster, more efficiently, and often more cost efficiently than ever before. As you can see, serverless computing has already made a significant impact, offering automatic scaling and pay-per-use models without the headache of managing underlying infrastructure. The market itself, valued at USD 17.2 billion this year, is projected to grow significantly, hitting a CAGR of 14.1% through 2030. This presentation will delve into how serverless AI is streamlining deployment, boosting resource utilization, and ultimately accelerating innovation. Let's begin. So, what exactly is serverless AI architecture? At its core, it operates on an event-driven model. This means computing resources are dynamically allocated only when needed in response to specific triggers. Think of it like a light switch. The power is only on when you flip the switch. The key components, as illustrated here, include event sources, function containers, supporting services, and finally, resource management. For event sources, these are the triggers I mentioned, things like API request, changes in data, or scheduled task. They initiate the process. Function containers. These are stateless environments where your AI model code actually executes. Stateless is crucial here. Each function invocation is independent, which is what allows for massive parallelization and seamless automatic scaling. Third, supporting services. These are essential backend components: authentication, data storage, monitoring, all managed for you. And finally, resource management. The platform handles the dynamic allocation of resources based on the workload demands. This architecture significantly reduces the burden of infrastructure management. In fact, organizations leveraging this approach have reported up to a 68% in reduction in infrastructure management overhead. That's a huge win, freeing up teams to focus on building great AI, not managing servers. Now, we understand the architecture. Let's look at how serverless AI solutions are typically implemented. It generally follows a cyclical pattern, as you can see in the diagram. Model encapsulation. First, developer package their machine learning models within their stateless functions. These functions are often triggered via HTTP request for inference points or other events. The beauty here is the minimal infrastructure code. Second, deployment. Next, this packaged function, which was created in model encapsulation, is pushed to a serverless platform along with its trigger configuration. Third, execution. When an event occurs, say an API call with new data, the function runs, performing the AI task like making a prediction. Scaling. And critically, the platform automatically allocates resources based on the demand. If you see a sudden spike in request, it scales up. When demands drop, it scales down. You only pay for what you use. Modern serverless platforms are quite versatile, supporting diverse ML frameworks and model architectures. We are seeing successful deployments of complex deep learning models ranging from 75 MB up to 1.8 GB, all while maintaining impressive performance, like an average inference time of just 112 milliseconds. Can you believe that? Okay, so of course, not all serverless platforms are created equal. Choosing the right one is critical for AI deployments, especially when considering performance, cost, and specific functionalities like GPU support. This slide presents a snapshot from standardized benchmarking studies that used identical deep learning models, ResNet 50, BERT-based, and YOLO v4 across major cloud providers. Let's talk about GCP, Google Cloud Functions, which is a product of GCP, standouts for an image classification workloads, demonstrating the lowest average inference latency at 112 milliseconds and also the fastest cold start time. Their GPU support is also quite comprehensive. For Amazon, AWS Lambda follows with a strong 136 millisecond inference latency, and their Snap Start feature significantly improves cold start time for Java functions with good but limited GPU support. Currently, it's on T4. Azure Functions for Microsoft offers the most consistent cloud cold start performance and container-based GPU supports. Last but not the least, ABM Cloud Functions. While a capable platform, currently shows slower inference and cold start times in these benchmarks and lacking direct GPU support for functions. Let's see, what's the key takeaway here? It is the cold start, the initial delay when a function is invoked after a period of inactivity. It is called as cold start. This could be a significant factor, especially for a GPU accelerated functions. Google Cloud Functions, for instance, showed a 58.7% faster initialization time for these. So depending upon your specific AI workloads, sensitivity to latency and the choice of platform matters greatly. Okay, so now let's talk about the key advantages of serverless AI. The benefit of adopting serverless AI are compelling and transformative. Let's look at some numbers here. It has 64.8% deployment time reduction. Imagine cutting your deployment model cycles from an 85 hours down to approximately 29 hours. This is a reality for many teams adopting serverless, a massive improvement compared to the traditional infrastructure. 79.3% resource utilization improvement. Serverless ensures you are using computing resources much more efficiently. No more over-provisioning servers that sit idle most of the time. 38.4% cost reduction. This directly translates to average savings compared to the traditional deployments, as you are only paying for the compute time you actually consume. 99.95% deployment availability. This high reliability is inherent in the managed nature of the serverless platform. So, to conclude, as mentioned earlier, automatic scaling capabilities are a game changer for various AI workloads. Platform can scale from handling 40 requests per second to over 4,200 requests per second in just over 3 seconds, all while maintaining the response time of under 23 to 35 milliseconds. This agility is incredibly valuable. Okay, so let's make this entire numbers concrete with a real world example from the financial services industry. A leading global investment banking was struggling with the scalability for their traditional risk analysis infrastructure. They had 38 dedicated high-performance servers, but they were operating at an average utilization of only 31.7%. So it's a classic case of over-provisioning and inefficiency. They decided to migrate to a serverless AI solution. The migration took about 4.5 months, and it wasn't without challenges. Adapting to complex workloads and ensuring regulatory compliance were key hurdles. But the post-implementation results were substantial. 68.2% reduction in infrastructure cost, a direct result of optimized resource utilization. 315% increase in the peak processing capacity. They could now handle over 12,000 concurrent model execution during the peak reporting periods, something unimaginable before. 62.2% improvement in the processing speed. Average latency for a risk analysis dropped from 8.2 seconds to 3.1 seconds. And crucially for finance, enhanced regulatory compliance through comprehensive audit trails and improved security protocols inherent in the new system. This case study clearly demonstrates the tangible business benefits of serverless AI in a demanding, regulated environment. Now let's take a real-life case study for another critical center, which is healthcare. A healthcare technology provider specializing in medical diagnostic tool faced a similar challenge. Their traditional server-based architecture for a medical image processing required significant upfront capital investment, specialized personnel, and suffered from a long infrastructure provisioning timelines, averaging 86 days to expand service. They adopted a serverless AI solution using containerized deep learning models. The migration spanned over 7 months, over 3 phases, with a strong focus on security, strict access controls, and comprehensive encryption. The outcomes were impressive. First, operational improvements. A 73.5% reduction in the operational overhead. Their auto-scaling capabilities now support variable workloads from 50 to 5,000 images an hour without any manual intervention. Deployment efficiency. The deployment cycle for a new model update plummeted from 36 days to just 4.8 days. This allowed them to rapidly integrate research advances into their production system. Financial impact. They achieved a 41.3% reduction in total expenses, despite a 212% increase in the processing volume. Imagine that number. Furthermore, the granular pricing models of serverless server allowed them to better serve smaller healthcare providers. Again, we are seeing serverless AI delivering significant improvement in efficiency, speed, cost, even while handling increased demands. Okay, so now let's talk about innovation and rapid development and how it helps there. Beyond operational efficiencies, a serverless paradigm fundamentally changes how organizations approach innovation and rapid prototyping in AI development. Organizations leveraging serverless architecture have on an average reduced their development cycle time by 57.8%. High performance teams are even seeing up to a 73.5 reduction in time to market for the new AI features. That's incredibly fast. Rapid prototyping in particular sees an impressive gains. Development teams can now deploy and test a new AI model variants in just 3.4 hours compared to nearly 23 hours in the traditional environment. This agility fuels increased experimentation, reduced complexity, improved collaboration, and accelerated time to market. You can see the numbers here. For increased experimentation, iteration speed can be increased by 2.9x, allowing for much faster validation of AI models and hypotheses. Teams have reported a 68.4% reduction in the implementation complexity, which also leads to decrease in your bug density by 52.3% and few post-deployment issues. Improved collaboration. Code reusability improved significantly with teams reporting a 53.2% improvement. Average feature deployment time dropped from 15 days to just under 5 days, with a high first deployment success rate of nearly 79%. So, it is safe to say that serverless empowers AI teams to innovate faster and more freely. Okay, so now let's talk about technical challenges and limitations. It's important to be balanced. Despite all the advantages which we have discussed so far, serverless AI isn't without its technical challenges and limitations. Cold start latency. This remains one of the significant issues. Complex deep learning models can experience significant delays up to 6.2 seconds during initial initiation. While platforms are improving, it is a factor to consider. Memory limitation. There are constraints on the model size and the complexity that can be loaded into a function's memory. Execution time limits. Functions typically have a maximum execution duration limits ranging from 250 to 850 seconds. This affects nearly 39% of the complex AI processing tasks that might be longer running. Vendor lock-in. Dependency on provider-specific features and services can make it harder to migrate between the cloud members. Imagine you started with GCP and then you wanted to shift to Microsoft in the between. Imagine the number of times and the number of hours you have to spend. Resource constraint. While scaling is automatic, the available compute options, your CPU types, memory configurations for individual functions might be more limited compared to dedicated virtual machines, especially for a very large or specialized model. In fact, over 82% of the enterprise AI deployments encounter at least one resource-related constraint. These are real considerations that organization needs to plan for when adopting serverless AI. Okay, now let's talk about security. Security is of course paramount in any AI implementation. Serverless introduces its own unique considerations compared to the traditional architectures. Isolation mechanism. Function isolation is a primary defense against the cross-tenant vulnerabilities. Container-based isolations used by many platforms provides effective security boundaries for a vast majority, nearly 95% of the common attack vendors. Access control. Effective identity and access management is fundamental. Around 69% of organizations are implementing fine-grained access control at the functional level, ensuring functions only have permissions they absolutely need. The use of short-lived credentials has been particularly effective, reducing credential misuse incidents by over 72%. Data protection. End-to-end encryption strategy for data at rest, in transit, and during processing are crucial and well supported by serverless platforms. Compliance, comprehensive logging, and monitoring capabilities are available, which are essential for meeting regulatory requirements and for auditability. While the attack surface shifts with serverless, robust security practices and platform features can effectively mitigate risks. Okay, so now let's talk about the future outlook. Looking ahead, the serverless AI landscape is set to evolve rapidly. We are expecting significant transformations in the serverless platform with increased specialization and optimization, especially for AI workloads. One exciting concept is nanofunctions. This represents a shift towards even smaller execution units, capable of executing specific components of a computational graph rather than the entire model. This could lead to more precise resource allocation, improved parallelization, and early results already showing a potential 37.8% reduction in the overall execution time. Here's a potential timeline of emerging trends. Let's quickly go over 25 to 26. We likely see standardized function interfaces and deployment specification emerge, which will help reduce vendor lock-in concerns. 26 to 27, expect an ultra-lightweight container format optimized for AI workloads. 27 to 28, predictive scaling algorithms could achieve a very high frequency in workload forecasting. 28 to 30, platforms will very likely incorporate more inbuilt capabilities for responsible AI, such as bias detection, fairness evaluation, and explainability tools. Therefore, the future of serverless AI is bright and full of innovation. Okay, so to recap, serverless AI offers a powerful new way to deploy and scale machine learning models, bringing significant benefits in terms of cost efficiency, speed, scalability, and fostering innovations. While challenges exist, the ongoing advancements and a clear value proposition make it an interesting, compelling choice for organizations across industries. Thank you very much for your time and attention. I'd be happy to answer any questions you may have. Thank you.